P.6 is rational expressions. All right, so let's talk first about what rational expressions are. A rational expression is the quotient of two polynomials. And don't you just love it when they use math words within a definition to define something else? Isn't that fantastic? What in the world is a quotient? Do you remember? Division. There's something about division with quotients, right? And in particular, when we're looking at these, we're going to see division expressed in fractional form. So this is very much going to look like a fraction of polynomials. So like a polynomial over another polynomial. The domain of such an expression is the set of all x values that work in the expression. And for these types, it's going to in particular mean values that don't make the denominator equal 0. I also love when you define things by what they don't do. Isn't that fantastic? It's such and such because it can't do this. Okay, these are the x values that won't work, right? The won't work things is what we're looking for. All right, so in particular, if you're looking for what won't work, then you're looking for, in this case, things that do make the denominator equal 0. Let's take a look at number 1. It's x squared minus 1 over x minus 5. What would make the denominator equal 0? 5. So now 5 would be not in the domain, and everything else would be in the domain. So let me show you one way of expressing this. The notation I'm about to show you has a name. It's called set builder notation. So for those of you who are a little bit artistic, and I'm definitely not, but curly braces, they're fun to draw. Draw a curly brace. It doesn't need to be as big as mine. I don't know why mine was so big. Because that was terrible. Let's go back to my big one. All right, here we go. You're going to write, I'm going to show you how to write it, and then I'm going to show you how to read it. You're going to do an x first. You're going to do a colon next. And then you're going to write x does not equal 5. You're going to show the things that it doesn't equal. Again, it's called set builder notation. The way that we read this is that this is the set of all x. In other words, it's all x values. The dots are read as the phrase such that. The set of all x values such that x does not equal 5. It's mathematical notation. It's a way of writing it. All x values that are not 5. It's good? Yeah, that's how it's written. Let's take a look at the second one. First thing to sort of take note of is it doesn't really look like a quotient, does it? It doesn't. It looks just like a polynomial, a binomial in particular from our last section, right? That's what it looks like. But what if I did this? Does it look like a quotient now? It does. It's got the fraction in there. By default, not very exciting, but by default, the number 1 is a polynomial. Not a very exciting one, but it is one. So this is a quotient, i.e. a fraction of polynomials. It fits the description, again, kind of by default. Okay? So we can still approach it in the same way. We ask ourselves the question, what x value would make the denominator 0? What was that? Infinitely many. I think you're answering the question the other way around. Nothing. Yeah, nothing would make the denominator 0, right? The denominator is a number, actually. It's already 1. There is no x value that I could put in that would make the denominator 0. That means, if you think about the way I wrote this over here, at the end there is no x cannot equal part, correct? It means x can equal all real numbers, anything. So what we would do is we'd write it like this. Curly brace, x, or the colon, such that x is any real number. That's the domain. Any real number. Any number is allowed in this quotient because no number will make the denominator 0. Number 3. What's that denominator look like? A what?
Crazy.
It looks crazy. It could look crazier. What kind of a value is that? What is that thing down there called? Trinomial. Very good. So it would be probably a long process of trial and error to check and make sure what numbers really don't work with it written the way it's currently written. Agreed? You might happen upon something, you might not. It would not be super easy. Somebody said something. Factoring would make it easier to make that decision, wouldn't it? Okay, now this is one that actually factors by guess and check really easy, and I haven't shown you a guess and check one, so we're going to do one just for fun, okay? So we're going to leave the numerator alone because the numerator has nothing to do with domain, okay? So we just rewrite it, leave it alone. On the denominator, we're going to have 2 sets of parentheses when we're done. The value at the front of the parentheses have to multiply together to give you x squared. There are only 2 values that will do that. X and x, if they're going to be smaller than they were originally, right? Yeah, x and x. The 2 numbers at the back have to multiply to give me 2. Again, it's 2 and 1. I don't have any choices. So that's why this is such a nice guess and check one. And the signs all the way across that denominator are positive. So the 2 signs down here are also positive. And you can see that it will work by multiplying the inner terms, 2x, right? The outer terms, 1x, and 2x plus 1x is 3x. So it does work. It's not just saying, oh, by default it's going to work all the time. It wouldn't have to, but it does on this one. Now, some of you have probably already done something you shouldn't have done. Some of you have probably canceled the x plus 2's out. Oh, somebody said, no, I didn't. It's good. Now, if the directions were different, and we will encounter different directions next time, that would be the next thing we'd need to do. If we want to simplify this expression, that's what we would do. But that's not the directions here, right? The directions are to simply find every x value that would make the denominator 0. And we don't simplify before we do that. Are there x values that make this denominator 0? Yeah, there are. What are they? -2 and -1. Either of those plugged in would make one component of the denominator 0, which would zero everything out. So, just like on the last 2, curly brace, x, such that you can either write x does not equal -2, x does not equal -1, or you could group those together at the end and simply write x does not equal -2, comma, -1. Either of those would be acceptable ways of expressing the same thing. Okay, so no simplifying before you decide on domain. Now, one thing to notice really quick, I'll make mention of it and we'll talk more about it later, is that if you were to graph this, these issues with the domain show up differently. One of those numbers will show up with an asymptote. The other one will show up, well, in fact, it won't show up on your calculator because your calculator can't do it so detailed, but it would be a hole in your graph. So the ability to cancel out affects what kind of problem actually is happening there, but it doesn't affect the fact that there is, in fact, a problem.